Hello, my name is Peyman Faryaz. I'm a PhD student at the CTU's Research Center of the University of Santiago de Compostela. I'm going to present today our work, which has been recently published in IEEE Transactions on Computational Imaging. In this work, we introduce a co-design of image sensor and processing techniques for indirect time-of-flight 3D sensors to effectively address challenges associated with multipath interference. Well, resolving MPI in ToF 3D imaging poses a significant challenge that requires sequential measurements at multiple frequencies, and this causes a reduction in frame rate. To address this, we've proposed a single-shot alternative incorporating low distortion Fourier sampling. So our initial focus is on introducing hardware that can provide multi-frequency measurements in a single shot. And this can be achieved by grouping neighboring pixels, each demodulating with different frequencies. This figure shows our proposed single-shot multi-frequency setup. A key difference with traditional systems is using short impulses for illumination, which can be ideally modeled as train of Dirac delta functions. Also, having different demodulation frequencies, which are an integer multiple of the base modulation frequency. The number of frequencies can also be altered or modified to suit the specific requirements or design considerations. And please note that the resulting single-shot Fourier camera acquires optimal measurements since the sinusoidal sensing functions are maximally uncorrelated with Dirac delta functions. Here we have the electrical simulation results of our system, which show the cross-correlation function of the illumination signal and control gate signals. The mathematical model also emphasizes our goal, which is recovering the scene response function. It's important to note that increasing the number of reflections add complexity to scene response function in Fourier domain. So basically, having more frequency measurements improves the accuracy of retrieved scene response function in time domain. In our specific iToF design, we are able to extract 16 complex numbers from 4-phase measurements, while in a single frequency setup, there's only one complex number where the phase shift can be recovered by the baseline 4-phase algorithm. In the second part of our work, we focus on procedures to recover MPI components from multi-frequency measurements. We use the matrix pencil method, which can estimate the parameters of sum of complex exponentials, and we also propose the inverse discrete Fourier transform with time domain super resolution. In our study, we have both qualitative and quantitative comparisons using the iToF to DToF image dataset. This figure shows two scenes from this dataset and their corresponding depth errors. Also, the table shows the effects of a number of frequency measurements on the accuracy of the retrieved depth. In the case of reflective MPI, we've tested two scenes with synthetic areas of two reflections. Here is another scene that has been tested for the case of 3 bounces. In all these scenes, the distances can be recovered in most cases with both methods. We have also conducted tests on the case of diffusive MPI, and as expected, the multi-frequency system performs better than the baseline approach, especially in the areas affected by MPI. In summary, we propose a novel approach to imaging by employing pulse illumination and especially multiplexing multiple frequencies across different pixels. Our system captures Fourier coefficients of the scene response function in a single shot. Also, the data processing method is general and holds for any number of reflections. Thank you for your attention. For further details, please refer to our paper.